All right, let's try this one. So we've got a cantilever beam that's got a uniform load partially, and then it's got a point load and a point moment applied at the end. We want to draw the shear force and bending moment diagram for that. So we need to start off with knowing our end conditions here. So we're going to have to do a little statics first. So I'm going to assume that I have a positive shear at A and a positive bending moment at A. So those are both the positive sign conventions for my shear force and bending moment. And we'll find out here in a minute if those are actually positive. So to do the statics for this, I'm not going to draw the free body diagram. I'm going to be a little lazy. I'm just going to use this and come back and get my concentrated equivalent force for that. And you can if you like.
Will we still be able to get that? Like the full answer?
Oh, you can. Yeah. So the question was, like on the exam, can you use my diagram as your free body diagram? You can, but a lot of times I don't give you a lot of space up above the diagram, so that you might. I don't have much paper as you guys have, because I've made it bigger and turned it sideways. But you could easily draw a line drawing for the free body diagram and do that. It might be better for you anyway. Be safer. Yeah?
Do we have to use straight edge on the test?
No. I just have to be able to read what you write. For some of you, that's a challenge. So. All right, so what's the area of this curve? It's a rectangle, base times height, 12 times 4. Looks like 48. And that'll be in kips. And measured from A, that'll be half the distance or 6 feet. So that should give me enough information to find those. So I'm going to come over here and using right-hand rule for my sign convention, I'm going to sum moments at A and make sure it's in equilibrium. So what kind of moment is this in my sign convention? It is negative. What kind of moment about A does this 48 kip equivalent force create? Positive or negative? Negative. So it's a force of 48 kips and a distance from A to the centroid of 6 feet. About A, what kind of moment does this 60 kip force create? Negative. So that's 60 kips. And the distance from A to there... Oh, I left off a number. This is 8 feet. Sorry. How do I know that it's 8 feet? I just made it up. I stuck 8 in there. You want it to be something else? Since I didn't give it to you, I'll just say it's 8. So that'll be a total of 20. That'll be a 20-foot moment arm. And then what have I got left? Oh, my moment out here on the end. What kind of moment is that with my sign convention? Negative. So that'd be a negative 100 kip foot moment. So from all that, I should be able to solve for the moment at A. It looks like it's going to be negative. I don't know what it is. 1,440. I just guessed. What's the answer? What is it? Oh, you guessed too. Somebody do this. What's 48 times 6 plus 1,200 plus 100?
That is 1,588.
1,588. And that will be kip feet. It came out negative, so we know our moment to start is going to be a negative bending moment. And then we can sum forces in the y direction. I'll assume up's positive. We should be able to find our shear. So my shear is acting up. That's positive in my sign convention. I've got my 48 kip equivalent force acting down. That's negative. And there's my minus 60 kip force acting down. So the shear at A is, looks like 108. and it's positive. Any questions about that?
Somebody came out negative.
If it came out negative, it means you start with a negative shear. Your diagram would start off at a negative shear value.
Does that mean like the MA that you've drawn up at the top,
Yeah,
that be reversed?
Well, I drew these because they're the positive values. So since I assumed positive and I got a negative, then I know it's a negative bending moment. So if I actually drew it on the diagram correctly, it would be the other direction.
Okay.
But I don't know that when I start, whether it's positive or negative, right? So I always like to assume positive and let the sign show up in the statics equation to tell me whether it's positive or negative. So now I can do my template. So there's where we're going to start. There's where we're going to end. I know something's going to happen here because my load is going to change from a constant to another constant, 0. So I'll add that location in. So let's do the shear diagram first. There's my positive x-axis. There's my positive shear axis. All these shears will be in kips. And let's start. So what do we know the shear at the beginning value is? That's the shear at A. We solve for that. It's 108. 108. What should the shear value at the free end be? We've talked before about these point loads at the end. If you can imagine a positive shear just to the left, remember positive shear on the left side is up. Just like here, left side is up. And let that little bit here, delta x, get as small as you want. It's going to be equal to the point load. So it'll be a positive shear. So I should expect a positive value for shear over here of 60. So I know where I'm starting. I know where I got to end. In between, I can use my relationships again that the change in shear is the area under the load curve, and that the slope of the shear diagram is equal to the load.
Will you want us to write that on like the
No, I do, but you don't have to. You know, one thing about these problems is besides just looking at them and having them check in with things that you know happens, there's really no calculations to write down. It almost looks like the diagram just appears on your paper. Almost like you've cheated, like you've looked at somebody else's paper and just sketched them down, right? I know you're not going to do that. But really, there's really nothing else. All the calculations are pretty minimal. Adding, subtracting. So you don't have to write. There's really no calculations out except for the initial reactions. After that, it just seems to appear. And I guess that's the beauty of this method. Of course, the downside with anything beautiful always has a downside. Right? You should learn that. That's a life lesson. And the downside is if you get it wrong, you got nothing. There's no partial credit in these if you get it wrong. I mean, it's like all or nothing.
What if you get the calculations right?
Well, this is the beginning. This gives you the endpoints. If you then draw a diagram that looks like this, that's wrong. So I can't do anything but to give you no credit for that. And of course, if your shear diagram is wrong, your moment diagram is by default also wrong. Unless you did look over at your neighbor and just sketch down theirs at the very end. And then I'll notice that you didn't do it. So don't do that either. So I find these problems very easy for me to grade. I don't have to think. They're either right or they're wrong. It's just like it's binary. Very, very simple. But you get them all right, then I won't have to worry about it. I want you all to be successful. Indeed. All right, so the change in shear, say the first 12 feet, should be equal to the area in the load diagram, which is a constant. It's a rectangle. Hey, we've already done it. It's 48 kips. Is that a positive change or a negative change? Negative. Down is negative, so if I take 108 and I subtract 48, what do I get? 60. What's the shape of the curve in between? Well, it's given by the load. And what is the load? It's constant, and it's negative. So here's a constant negative slope. And again, just to bring that home, I'm going to write that it's 1 to negative 4. It's equal to the loading. So if I ask you, what's the slope of the moment of the shear diagram at x equals 6, what would you do? You would go over here to x equals 6, and the slope of the shear diagram is given by the load. What is the load? Negative 4. I just want to know if you are actually interpreting the data. Now the change in shear from, say, 12 to 20 is the associating area in the load curve. And what's the load curve over that 8 feet? 0, no change. 60, say 60. And the slope is given by the load, and the load is 0. So 0 slope is that. So there's your shear diagram. It's got like a trapezoidal section, and then it has a constant section. I feel pretty good about that. So now let's draw the moment diagram. So there's my positive x, my positive moment. This will be in kip feet for my units. And what's the moment at A? The bending moment at A. Did we solve for that? We did. And what is it? Negative 1588. Do we know the bending moment anywhere else? No. What's the bending moment out here at the free end? What kind of bending moment is that? Positive or negative? Negative. That's a negative bending moment. So that means we're going to hit negative what? 100. 100. So there's my starting point, there's my ending point. And in between, the change in moment is the area under the shear diagram. And the slope of the moment at any point, given by the derivative, is the value of the shear. So let's see if we can get the change in moment over the first 12 feet. That's what this is telling. So what's the area under the shear diagram from over the first 12 feet? It's a trapezoid. What's the area of a trapezoid? You average the height times the... hey, it's hard for me to talk over you guys. Can you guys shut up? Thank you. So what's the average of a trapezoid? What's the area of a trapezoid? Sorry, I didn't mean to tell you to shut up, but I did. So, sorry. So what's the average of 108 and 60? I think it's 84. And what's 84 times 12? I can't do that in my head. Actually, I can, but I won't do it.
84 times 12?
12, yeah, the base.
1,008.
1,008. So 5888 minus 1,008 is... 508? 80? 588?
No, sir. No, 580.
580.
Yes.
I like that. What's the shape of the curve in between? I don't know what it is. All right, so what it is, the shape of the moment diagram is the shear. So what's the value of the shear right here? Positive 108. So I'll just draw something positive. And it gets smaller to positive 60. I'll just say this is positive 60 right there. They're both positive. See that? They're both positive, right? One's larger going into one smaller. So that should give me the shape of the diagram. Parabolic. So now the change in the moment from 12 to 20 is the area of the shear diagram. What's the area of this shear diagram? Yeah, it's 8 times 60. That's both positive. That's 480. Oh, I messed up. This is negative. So negative 580 plus 480, what do you know? It gives you minus 100. And what's the slope? Well, it's equal to the shear, and the shear is constant. So it should be a kind of a straight line. So that's kind of linear, not kind of, it is linear. And then this is quadratic. So I could ask you, what is the moment at x equal 12? And you would say, negative 588. I could ask you, what's the maximum moment in the beam? And you would say, and where does it occur? At A. I could really mess you up. I could say, what is the slope of the moment diagram at x equals 6? What is the slope of the moment diagram right here at x equals 6? Slope of the moment diagram is shear. What's the value of the shear at 6? That's midway through the point. It goes from 108 to 60. What's that? It's 84. Positive or negative? Did you guys miss that? Yeah. At 6 feet, what's the slope of the moment diagram? What's the slope right there? The slope of the moment diagram is equal to the value of the shear. What's the value of the shear at x equals 6? What is the value of the moment diagram? The shear diagram at x equals 6. What's right in the middle? It's 12. So what's halfway between 108 and 60? 84. Is that too sophisticated? What's the slope of the moment diagram at x equal 19? Right here. What's the shear at x equal 19? 60. So don't forget these things. They come in handy. They don't only help you build the structure. They might actually help you answer the questions. So, most of these, I give you 4 problems on the exam, so they're each 25 points apiece. Like on a problem like this, I would probably give, say, 10 points for these 2, and the remaining 5 points would be if you could read data off the graph.
So you said there's 4 questions, or 4 total questions, or 4 shear and moment?
There are not 4 shear moment questions.
So there's one.
I'll talk to you about that on Tuesday. I'll tell you what's going to be on the test.
Okay.